So let's move to the third section, concentration-dependent diffusivity. In previous cases, when we talk about the diffusion process in solid materials, we first the fixed second law. We mentioned actually we make a very important assumption is the diffusivity equals to constant, but if the diffusivity is not constant, it changes with concentration of the diffusing species. Then how to get the diffusivity? How to obtain the diffusivity? Here we are going to introduce a method we call Boltzmann-Matano analysis to obtain or to determine the interdiffusivity. And what's the Boltzmann-Matano analysis? So first of all, we need to consider now we have a diffusion couple A bind with B, and if you try to plot the concentration profile of A, then you will get this step profile in green. And this is when T equals to 0. That means before diffusing happens. Then you can get this concentration profile, right? Then as long as you heat these materials up and allow the diffusion happens, then you can get these curves, this profile of diffusing atoms or this profile of Ca. Then next we are going to try to identify the boundary condition here. For these diffusion couples at negative infinity, if we assume the interface here x equals to 0, then at this location it is negative infinity, then the Ca equals to C0. And partial C partial x equals to 0 means the concentration profile of A does not change with time at negative infinity, because it at negative infinity it already far away or much longer or larger than diffusion distance. Okay, and because iota is a function of x, so the partial C partial eta also equals to 0. Then this is at negative infinity. Then take a look on the boundary, right-handed end of this diffusion couple. The boundary condition here, Ca equals to 0, and the partial Ca partial x equals to 0. That means at positive infinity, which is far away from or much larger than diffusion distance. So the concentration profile of Ca does not change with location. And also, because iota is a function of x, so the partial C partial eta equals to 0. And this is a diffusion equation we derived from continuity equation. Now the diffusivity is no longer a constant, it's a function of concentration. So we cannot just take this D diffusivity out of this operator. So we need to solve this diffusion equation. And the method to solve this diffusion equation is we land a scaling variable iota equals to x over square root of t. And after serious deviation, we are going to introduce you in next slide. Then the results shown here is the interdiffusivity is a function of concentration of Ca. And what's the interdiffusivity D? How this interdiffusivity changes with concentration, Ca. The result demonstrates that can be divided into 3 parts. The interdiffusivity at this concentration Ca or C' changes with diffusion time period T, and also the slope of partial C partial X is the slope of partial C partial X. It's a concentration gradient at C', but it is a reciprocal of concentration gradient at C'. This is the second part. And the third part, which is the total number of diffusing atoms you integral from where? X times, X is the location, right? Times the numbers of diffusing atoms, Ca, from 0 to C', means you integral from here, you integral along C is a integral from 0 to C'. It's like this. Integral to C'. Then is the area of this area. Okay, so this is implying that the diffusion time period and the concentration gradient at your interesting concentration, and also the total numbers of diffusing atoms you integral from C0 to C'. These 3 factors will change the interdiffusivity at C'. That also implies that as long as we have this diffusion profile of diffusing atoms at each location, we got the different interdiffusivity, because even they have the same time period, diffusion time period, but the slope and also the integral term are different. So that means interdiffusivity at this location, each locations on these curves, the interdiffusivity are different. Okay, and by using this equation, you can get the interdiffusivity at specific concentration of diffusing atoms. Okay, so next slide is going to show you how to derive these equations. So in order to get the interdiffusivity as a function of concentration, so we lent a scale variable iota defined as x over square root of t. And some people probably will ask, in previous slide, we lent iota equals to x over square root of 4dt. Why here we just lent it a square root of t? Because we need to get d. So we cannot lent iota equals to x over square root of 4 dt or dt. Otherwise, d will be deleted. So we are not going to have a diffusivity as a function of concentration. So after setting this variable iota, then the following process like this, we try to convert this equation to what? To partial c partial iota. This is 2 variable, right? But we try to convert it into 1 variable iota. So that's how we deal with. And so next step, we are going to deal with the left-handed term. It's partial c partial t, and we use the chain rule. So partial c partial t, partial t partial iota, partial c equals to 1. That's what is the chain rule, right? We mentioned in previous slide. So we just move the two terms to the right-handed side, and partial iota, partial t, iota, you partial iota, partial t. So you got this results, and keep this partial c, partial iota here. And let's deal with the right-handed side. It's a partial c, partial x. Partial c, partial x, we use the chain rule as well. And partial iota, partial x, so you only left 1 over square root t. And just copy this term. Then we just inserted both results into this diffusion equation. And one thing probably will you need to pay attention would be before you inserted these results, you need to deal with the right-handed term here, right? So I use different colors to label that. Diffusivity, partial c, partial x is what we get here. So you inserted these results, and now you get this results, right? So you need to partial this term d times partial c, partial iota. You cannot just take the diffusivity out because d is a function of c. So what can we do here? We can just partial d, partial iota times this term plus diffusivity, partial this term with iota. So this is what we deal with here. So the left partial c, partial t equals to this term, right? So copy our left-handed term. And the right-handed term is what we mentioned, is you partial d, partial iota times the rest of term plus diffusivity times and partial this term with iota. And you just simplify as this one. Simplify this term into this one. Then you delete the iota or drop this term, the iota term, and integral both sides from where to where. From when you integral, so you need to know the bottom limit and upper limit. So integral for the c dc will be from 0 to c prime. So turn the bottom c to c prime. So you get the integral and c to c prime. So you got this term because you did this one. So you got this 0 c prime. So after arrangement, you can get the interdiffusivity. How the interdiffusivity change with concentration will be associated with diffusion time period, the reciprocal of concentration gradient at C prime, and also the total number of number of diffusing atoms integral from 0 to C prime. Okay, so this is just a mark something. So based on this result, it's quite easy to you to directly use this result to get the interdiffusivity at different location in this diffusion couple, right? As long as you get this curve. So some people probably will ask how to get this profile, diffusion profile. In your experiments, first of all, as long as you have a diffusion couple, when you heat it up and allow diffusion happens, then after time t, then you just section. You try to section this diffusion couples and using element analyze equipment, for example, like the EPMA or EDEX or SIMS, to get the concentration profile of A. As long as you got this profile, then diffusion time period is what you deal with, right? You know that. And also, as long as you got this profile, you can get the concentration reciprocal of concentration gradient at any location, right? And the last part will be you need to, as long as you determine at C prime, you need to you need to take the integral, you need to know the total number of diffusing atoms within this region, right? But there's one more missing information, is where is x, the point at x equals to 0. As long as we locate x, the point of x at 0, then you can get this integral. You can get the value or integral value of this term, right? But where is x equals to 0? Is this plane equals to the original interface plane? Or how to define this plane? The answer is not. This plane x equals to 0 plane in this case. While the diffusivity changes with concentration, this plane is not equals to the original interface. So let's tell you, next slide is going to show you how to locate this plane of x equals to 0. So this plane, we call it is a Matano interface. X equals to, this is a plane, x equals to 0. This plane interface is not really a visualable interface. You cannot see it in in a diffusion couple. It's just a mathematical defined interface. So what's the mathematical defined interface? This plane has some physical meanings. The quantity of A atoms moves from A side is equal to that ended in the B side. So that means after t time period t, you got this profile, right? And the quantity of A moves from A side. This region is a quantity of A atoms move from A side, right? And this region, these atoms, total atoms will be equals to the atom ended into B side, and the plane, this plane, we call it is a Matano interface. So it is really a mathematic defined plane. So in order to know how to get this plane, we grab the equation we derived from this. We just grab this results. We get this results here. So integral results. So okay, iota dc, right? This is the result we get here. But we change the button. We change the limit. Which we change the C prime to C0. So that means we integral. We just change the upper limit to C0. That means we integral. So it is the iota dc, right? And we integral from here to here. We integral the whole diffusion couple along C, right? Integral from here to here. And if we use this term C equals to C0 minus C equals to C, then you will get the 0. So based on this, you can get the relationship the x times dc from 0 to C0 equals to 0. This plane, we call it as a Matano interface. It's reasonable, right? This area will be identified with this area. So when you take the integral, x is the location, right? On your right-handed side, the x will be positive. On the left-handed side, x will be negative. So when you integral from this side to this side will be equals to 0. So you can easily determine what's the x equals the point of x equals to 0. Okay. So let's give you an example here. Assume the interdifusivity D, which means the interdiffusion between A and B elements in the laboratory frame. So why, in this case, in this diffusion couple, the diffusivity we measure is interdiffusivity, because we measure at the laboratory, in the laboratory frame, right, instead of in the crystal frame. And we assume this interdiffusivity is a strong function of concentration B. So, given the diffusion couples A and AB alloy, which is annealing at high temperature for a time D, how does the interdiffusivity change with CB? So after diffusion or after time T, then we section this A and AB alloy diffusion couples and measure the concentration profile of CB along with these materials, these diffusion couples. Then you got this profile. And how does the interdiffusivity change with CB? Based on the questions, you know the interdiffusivity is a structure function of CB. Is no longer a constant, it's a function of CB. So based on the equation you derived in previous slide, we know the diffusion time period T, and interdiffusivity is a strong function of CB. So this should be CB, right? Will be related with the concentration gradient of CB, reciprocal of concentration gradient of CB, right? So based on these curves, we know the slope at this region, concentration gradient at this region is small. After taking the reciprocal operation, then you got the interdiffusivity, and I got this term should be higher, right? And at this region, the concentration gradient is high, but take a reciprocal operation, then this term should be small, right? And we still have the third term to change the interdiffusivity. But as we mentioned before, if you try to submention the total numbers of diffusing atoms, usually this diffusion process, we assume it is a dilute dopant, right? You consider as a dilute solution. So the total number won't change as much. This term won't similar. But as you know, the slope locate, always is in between 0 to 1, and slightly changes in slope. The value for slope changes a lot. So usually this term dominates the value for the interdiffusivity. So in this case, this region has, because the slope, the gradient is small and take the reciprocal, so you got a large interdiffusivity. This region, you take the reciprocal of gradient term, so you got small interdiffusivity. And so that's this result can explain why you observe more CB penetrate more at this region instead of in this region, because the interdiffusivity D is large, so you can observe more B atoms penetrate into deeper region. Okay, the penetrate more here. Okay, so let's try. I try to draw some pictures to explain the difference between while the diffusivity equals to constant and the diffusivity is a concentration dependent case. So now we also have a AB diffusion couple. If the D is equals to constant, so this is AB, right? For example, and you got the interface is the original interface, and after time t, you can measure the concentration profile in green. If D is constant, and the Matano, and you can observe this curve. This profile is a symmetry curve. And the original interface is the Matano interface, because this region will be always equals to with this region. So the original interface will be the same with the Matano interface. But however, if the diffusivity is a function of concentration, changes with concentration, and the profile you can get probably is like this blue curves, and you need to, and at this moment, you need to re-identify the Matano interface, because this phase allow the region, the area here will be equals to area here. So you need to relocate the Matano interface. And this Matano interface is not the original interface anymore, due to the concentration changes with, diffusivity changes with concentration. Okay, so in order to make you more clear, so I draw the AB diffusion couple, and this is the original plane. So some people, in order to identify the original plane, some people will put some markers here. You can use a laser to make some holes here, and we assume JA larger than JB, so you can get the vacancy flux to the left-handed side. So after diffusion, as based on the Kirkendall effect, this original plane, this plane is going to shift toward to where? Because JA larger than JB, so it's more A moves here, so it's going to push this original plane to a left-handed side. It will be like this. And if D is constant, then you can, after time t, then you can plot these curves, right? So, and as we mentioned, because diffusivity equals to constant, so the Matano interface will be the same with marker plane or original plane. And also, as long as you locate this one, this plane definitely satisfies the atoms moves from A side equals to that ended into B side. So this area will be the same with this area. And because this curve is symmetry, so this concentration will be Ca over 2. But however, if diffusivity changes with concentration, then the curves is not symmetry anymore. Then you need to relocalize the Matano interface to allow this area will be equals to this area. And some people probably will ask, at this region, where's the marker plane or original plane? It's definitely somewhere at left-handed side. As long as you do the experiments, then you can observe the moving of the marker plane or original plane. But as we mentioned, Matano plane is a mathematics plane. You cannot see it. It's just a mathematical plane to help you to what? Help you to calculate the interdiffusivity, the value for interdiffusivity at different location. Just help you to define the value of interdiffusivity, because you need to know where is the 0. Then you can get this value, right? So let's see why we need to know where is the Matano interface. Just help you to define the value for interdiffusivity. Okay, so let's move to the last section, is an anisotropic diffusivity. diffusivity sometimes changes with concentration, temperature, but the diffusivity also changes with crystal symmetry. So crystal structure definitely will affect the diffusivity. Why? Because what's the diffusivity? Diffusivity is the physical entities to describe how a diffusing atoms moves along or in your materials. If your materials is anisotropic or a symmetry crystal structure, and the moving speed or moving velocity definitely changes, right? And not only different crystal structures, if your materials is polycrystalline grains and the grain bond you contains grain and grain boundary, it definitely effective the diffusivity of this material, right? So anisotropic of diffusivity, for example, like we have a graphite. The thermal conductivity is to describe how the heat transport through this material, right? The thermal conductivity along the plane of graphite on the same plane is 355 watt per meter K. But if vertical, that means across different layers of graphite, you can see the thermal conductivity drop to around 90 watt per meter K. So that tells you this is graphite is an isotropic crystal of isotropic materials, right? So in previous slide, we only we always tell you that the fixed first law can express like a flux equals to atomic flux equals to minus diffusivity times the concentration gradient. And we apply this fixed first law in isotropic materials. At this moment, D is a scalar, right? But when we have an isotropic crystal, we cannot just use the one D to represent the diffusivity, right? We need to depart it into different S's. So if we deal with an isotropic material, then we need to modify the fixed first law like this and use this diffusion tensor to represent the diffusivity along different axes. So for example, like if we assume this is three-dimensional, always the materials we deal with is three-dimensional materials, right? So we should have a J1, J2, and J3, and based on the diffusivity diffusion tensor, we got the 3 times 3 diffusivity tensor, and also corresponding to concentration gradient will be along x1, x2, and x3. This we call the diffusivity tensor, and this diffusivity tensor is highly related to crystal structure, and so you are going to get the J1, J2, and J3 alone in your materials. And as you know, there are 3 times 3, so we got 9 parameters in diffusivity. In order to simplify it, we use the Ansaka symmetry. So we assume D12 equals to D21, and D23 equals to D32, and also D31 equals to D13 equals to D31. So we can simplify the diffusivity tensor from 9 unknown parameters down to 1, 2, 3, 4, 5, 6, down to 6 unknown parameters to simplify this diffusivity tensor. And as long as you have this complex diffusivity tensor, how to make the flux or the diffusion, because as long as you got this kind of complex diffusivity tensor, the diffusion equation you have is more complicated, right? So that we are going to use, as long as you got 3 times 3 diffusivity tensor, we try to do the coordinate transformation, and the original axis will be x1, 2, 3. Then we want to convert it or transfer to principal systems, x1 hat, x2 hat, and x3 hat. So how to do that? So you can solve the eigenvalue for this 3 times 3 diffusivity tensor, then get the lambda 1, 2, 3. Then as long as you get the lambda 1, 2, 3, then you can get the converted to this d hat as like a 3 principal system. Then that will help you to simplify the diffusion equation, becomes to this, which much simplified. I mean, it's much simple to allow you to solve the C, right? Okay, so this is how we deal with when you have a diffusivity tensor, how to simplify it. You just simply convert it to principal system. Then that will allow you to get a much simple diffusion equation. Okay, by getting the eigenvalue for this diffusivity tensor. Okay, so isotropic of diffusivity. Let's move to an example. So isotropic materials. What is the isotropic materials included? Isotropic material means the diffusivity along x, y, and z are the same, right? So you use the d scalar value to representative this diffusivity. And isotropic material included the amorphous solid glasses and the randomly orientated fine-grained polycrystals. And for example, like the cubic structure included FCC, simple cubic, body center cubic, and the diamond cubic. So for these 4 crystal structures, then we can use the d scalar to represent it. And when you try to formulate this diffusivity isotropic material into this diffusivity tensor, then you will find that you only have you don't have a D1, 2, D3, 2, and D2, 3, and only have D1, 1, D2, 2, and D3, 3. That means the diffusivity along axis 1, diffusivity along axis 2, and diffusivity along axis 3. And as you know, this cubic structure, the axis 1, 2, 3 are what? Perpendicular to the other one, right? So the angles between axis 1 and 2 is 19 degrees, and also the angles between 2 and 3, axis 2 and 3 is 90. So, and also the same angles between the 1 and 3, right? So, and as you know, they are fourfold symmetry, and x1, 2, 3 are perpendicular to each other. So that allow, when you try to formulate this kind of cubic structure into diffusivity tensor, you got the 0, 0, 0, 0, 0, 0, and D1, 1 equals to D2, 2 equals D3, 3, because the atoms moves along 1, 2, and 3 are the same. I mean, the velocity of moving species along 1, 2, and 3 are the same. Okay, so as we summarize the anisotropic of diffusivity for different crystal structure, and you can take for this, you can take this slide for reference. For example, like tetragonal, also we know tetragonal is A equals to B, not equals to C, right? But the axis the angles between A, B, C, I mean X, Y, and Z are perpendicular. So we don't have these values for diffusivity. And D11 equals to D22, but not equals to D33 because A equals to B, not equals to C. Use the same idea for orthorhombic structure. The angles are all the 90s, but A not equals to B, not equals to C. So you got 3 diffusivity along different axes, but the rest of part equals to 0. For monoclinical structures, we A not equals to B, not equals to C, so we have less 1. And also alpha equals to gamma equals to 90 degrees C, but not equals to beta, so we have this value for D13. Okay, so this you don't need to memorize all this. You need to have some pictures and image for of the you need to have some list images and know that if your crystal structure is anisotropic, you need to modify the diffusivity into the diffusivity tensor. And this will be highly related to different types of crystal structure. The most important thing is the symmetry of these crystals. Okay, so let's give you a summary. Interdiffusion analyze, you need to have some pictures. What's the difference between the diffusivity is constant and the diffusivity will change with concentration? And in order to solve the concentration dependent diffusivity part, we need to know the Boltzmann-Matano analyze to get the interdiffusivity at different concentrations. You got the equation, right? And also you need to know, as long as you have an isotropic crystal structure, that will lead you an isotropic diffusivity, and how to modify the diffusivity. You need to use the diffusivity tensor, right? And based on different material system, then you got a different diffusivity tensors. And the more detailed parts, how lattice constant changes affect the diffusivity, we are going to introduce you in next lectures, lecture 4. Okay, so you just have some roughly image about this. An isotropic crystal structure definitely will lead to an isotropic diffusivity. Okay, so today let's end it here.